So let's talk a little bit about exponent functions and log functions. I mean, first of all, um, understanding how an exponential function might look is crucial. So let's talk about the situation here. We got a country, an imaginary country, with a population of 1.5 million people, increasing at a rate of 3.5%. Now, we can figure this out 1 year at a time without much trouble. If we start out at 1.5 million, you know that you're going to take the 1.5 and we can say equals, and we're going to take this and we're going to multiply it by 1.035 for 100% plus 3.5%. Okay, and we get this. Okay, now if we want to find out what at year 2, we're going to do the same thing. We're going to take this, we're going to start with this year's population from year 1, and we're going to multiply it by 1.035. Okay, and we're going to get this, and we can set this to round to let's go to 4 decimals. We can set that easily enough. Format. Maybe I can't. Maybe it's over here. Format. Number. Whoops. And we'll go to 3 decimals. Let's go to 4 decimals. Okay. And we'll go ahead and leave it at that. Okay. So now it'll be at 4 decimals. Okay. Now, if we want to keep doing that, I can actually copy that function, which is just going to take the previous year's population and multiply it by 1.035, and we can drag that down, and that'll be that. But what did we do each time? We took this first population, multiplied it by 1.035, then multiplied by 1.035, then multiplied by 1.035. So we've got an exponential function. We can actually say that that is equal to 1.5 times, I'm going to put the time sign in there, 1.035, close the parentheses, raised to the, this, now I'm going to that power. It's going to give me an error because I don't have this as a value, but I'm going to go ahead and, okay. Now it will give me that. Now, if I take this function and drag it down, whoops, come on, grab by the corner, pull, okay, and let's format that to 4 decimals also, and those look the same. So in this case, I just, instead of doing it 1 year at a time, I can find out, so what happens if I add a column, a row rather, and I want to find out what it is in year 50. Okay, I know now, it's 8.3. Now this one, I can't do that. I'd have to multiply 50 times, one at a time. So now I have an exponential function. Let's look at this. This is a graph of the exponential function. Okay, in year 0, it was 1.5 million. If these are in millions and these are years, okay, year 20, it was up here. So what happens now if I want to know when exactly does that population reach, let's say 4 million? Okay, now we can look at it and say, okay, well, I don't know, somewhere in here, somewhere, I don't know. Okay, well, let's find out when does y equal 4, and we could find out when the intersection of that is, and it's right at, well, did it do it? No. Oh, I know what I didn't do, okay. Intersect the two functions, and it's going to be at the year 28 and a half, about 28.5 years, it'll reach 4 million. Well, how are we going to solve that in a different way? Let's find out. If I want to look at that as a log function, I've got I know that y, the population, is going to be equal to 1.5 times 1.035 to the x power, where x is equal to the year. Okay, so what do I do? Well, I want to find out when is y equal to 4. When does 4 equal 1.5 times 1.035 to the x? Well, if I divide both sides by 1.5, I get, 4 over 1.5 equals 1.035 to the x. If I take the common log of both sides, okay, I should have written this differently. I can use the rule about the exponent to bring it in front, and I get log of whatever 4 over 1.5 equals x times the log of 1.035. I can divide both sides by the log of 1.035, and all of a sudden I have x is equal to the log of 4 over 1.5 divided by the log of 1.035. So let's see if we can do that. Okay, we're going to say parentheses. This calculator's a little different than the ones you use in class, but we're going to take that division, and then we're going to take the common log of it, not the log base 2, which is unusual to find that on a calculator. Okay, there's that. Okay, I'm going to write that down just because I don't want to lose it. 42596. Okay, and then let's find out what 1.035. Take the log of that. That's 0.01494, and let's say point. Let's clear this. Make sure we got that right. 0.42596 divided by 0.01494, and what do we get? Oh, look at that! Does that look familiar? It certainly does. 28.511, and we did that with a calculator. So that's the usefulness of a log equation if you don't have a nice tool like GeoGebra handy, and sometimes even if you do. I will certainly post more examples like that, but hopefully that helps you understand the usefulness of being able to work with logarithms. That's it for now.